Pluto is 3.67 billion miles from Earth. At that distance, even a radio signal traveling at the speed of light takes more than just to make one single trip. No human being has ever been there. Only one spacecraft has ever flown past it. And that was a single flyby that lasted a matter of hours before the probe kept moving and never came back. For decades, scientists accepted that Pluto would remain one of the most mysterious objects in our solar system, simply because the technology to study it properly did not exist. Then James Webb arrived, and what it found when it finally pointed its mirrors at this frozen, distant world was so unexpected, so completely outside what any model had predicted, that the lead researcher on the study stood in front of his colleagues and said the words that stopped the room cold. This is unique in the solar system, not rare, not unusual, unique. In all of recorded astronomy across every planet, every moon, every object ever studied in the history of human science, nothing works the way Pluto works. And that was just the first discovery, because by July 2026, James Webb had found something else at Pluto, something sitting on its surface that appears on at least one other world in the solar system simultaneously and matches absolutely nothing in the entire database of known chemistry. Scientists cannot identify it. Not yet. And this is the full story of how we got here, what James Webb actually saw, and why a frozen dwarf planet billions of miles from Earth may hold answers to questions about the origin of life itself. To understand why James Webb's observations of Pluto are such a massive deal, you have to start with what Pluto actually is, and how little we properly understood it before this telescope existed. Pluto was discovered in 1930 by a young astronomer named Clyde Tomb, working at Lell Observatory in Arizona. He found it by comparing photographic plates taken nights apart and noticing a tiny point of light that had moved, the classic method of detecting objects in our solar system. For 76 years after that discovery, Pluto was classified as the 9th planet. Then, in 2006, the International Astronomical Union redefined what a planet is, and Pluto was reclassified as a dwarf planet, a decision that caused more public outrage than almost any scientific decision in recent memory and is still debated inside the scientific community today. But the classification argument, entertaining as it is, was never really the most important question about Pluto. The most important question was what Pluto actually was, what was happening on that distant surface, what its atmosphere looked like, whether it was geologically active or frozen relic, unchanged since the early solar system. And for most of the time, since its discovery, those questions simply could not be answered because Pluto is too small, too far, and too dark for any telescope on Earth or in low orbit to resolve in meaningful detail. Even Hubble, the most famous space telescope of the 20th century, could only produce blurry, pixelated images that showed the vague outlines of surface features. Astronomers knew Pluto existed. They knew its approximate size and mass. They knew it had a moon called Charon, discovered in 1978. They knew it had a thin atmosphere detected in 1988 when Pluto passed in front of a background star and dimmed it in a way that proved something was there. But the actual nature of that world was a mystery. Everything changed on July 14th, 2015. After more than 9 years of travel across the solar system, NASA's New Horizons spacecraft made its closest approach to Pluto, coming within 7,800 miles of the surface and returning images and data that rewrote the textbooks overnight. What New Horizons found was not a dead frozen rock. It found a world of extraordinary complexity. Nitrogen ice plains so flat and young that they must be geologically active, constantly renewed by some process that shouldn't exist this far from the sun. Mountains of water ice rising 3 kilometers above the surface. A bright, heart-shaped basin now called Sputnik Planitia that has become one of the most recognizable features in the outer solar system. And an atmosphere, thin, layered, wrapped in blue haze that scattered sunlight in a way that made Pluto's skies the same color as Earth's when viewed from the right angle. New Horizons proved that Pluto was active, alive in a geological sense, doing things that no model of a small, icy body in the outer solar system had predicted. But New Horizons was a flyby. It had hours of close observation, not months or years. Its instruments were designed for a mission planned in the 1990s and launched in 2006, which meant they were excellent for 2006, but had fundamental limitations in what they could detect and measure. The biggest limitation was in the infrared. Pluto's atmosphere and surface chemistry leave their clearest signatures in mid-infrared wavelengths, the part of the electromagnetic spectrum that reveals heat and molecular composition in ways visible light simply cannot. And no instrument sensitive enough to detect those signatures at Pluto's distance had ever existed. Astronomers wrote papers about what they expected to find if such an instrument ever became available. They built theoretical models, they made predictions, and then they waited for James Webb. The first observations of Pluto using the James Webb Space Telescope were made with its MIRI instrument, which operates in the mid-infrared, a spectral range that had been completely unexplored for the Pluto-RN system due to the insufficient sensitivity of every previous instrument ever built. Results were published in 2 papers in April and June 2025 in the journals Astronomy and Astrophysics and Nature Astronomy by an international team led by researchers from CNRS Paris Observatory and the University of Reims, Champagne-Ardenne. Before getting to what they found, it is worth spending a moment on why mid-infrared matters so much for Pluto specifically. Infrared astronomy is essentially the study of heat. Objects emit infrared radiation based on their temperature, and different molecules absorb and emit infrared light at very specific wavelengths, like fingerprints. When you look at an object in the infrared, you can identify exactly what chemicals are present on its surface or in its atmosphere by matching the absorption and emission patterns to known molecular fingerprints. The mid-infrared range, from roughly 5 to 27 micrometers in wavelength, is particularly rich for the kinds of organic chemistry and icy compounds expected on Pluto. But detecting those signals from something as cold, small, and distant as Pluto requires sensitivity that is almost impossible to engineer. James Webb achieved it, and what the data revealed was nothing like what the models had predicted. Back in 2017, a planetary scientist named C.J. Zhang at the University of California, Santa Cruz, published a hypothesis. He proposed that Pluto's atmosphere was not primarily controlled by its gases, the nitrogen, methane, and carbon monoxide that make up the bulk of what's there. He argued it was controlled by haze, fine organic particles suspended high in the upper atmosphere, absorbing sunlight and radiating it back as heat, acting as a kind of planetary thermostat. He and his co-authors predicted that if this haze was cooling Pluto the way they thought, it should be emitting strong mid-infrared radiation, and that an infrared sensitive telescope should be able to detect it. It was a crazy idea. Jung said nobody could test it in 2017. The telescope that could test it didn't exist yet. When James Webb's observations were finally analyzed in the papers published in 2025, the results confirmed Jung's prediction completely. Pluto's atmosphere contains haze particles that rise and fall as they are heated and cooled, and those particles control the energy balance of the entire atmosphere as they heat up and cool off. That's very unusual and hasn't been seen at any other solar system world. The lead researcher on the analysis, Tanguy Bertrand of the Observator, stated plainly, "This is unique in the solar system. Every clears throat. Other atmosphere ever studied on any planet, any moon, any body, anywhere in the solar system is primarily regulated by its gases. Pluto is regulated by its haze. A layer of tiny solid organic particles suspended in the upper atmosphere is doing what nitrogen does on Earth, what carbon dioxide does on Mars, what ammonia does on Jupiter. It is the thermostat. It is the dominant controller of the planet's climate, and nothing like it has been found anywhere else. The haze is cooling Pluto's upper atmosphere by about 30 degrees C, more than any previous model predicted. On a world where the surface temperature is around 230 degrees C, that is an enormous effect. It means every atmospheric model ever built for Pluto was wrong in a fundamental way. Not wrong about the gases or the surface chemistry, but wrong about what was driving the system. The driver was invisible to every instrument that had ever looked at Pluto before James Webb. But the haze discovery, extraordinary as it is only the first layer of what JWST revealed. Because while it is cooling Pluto's upper atmosphere, the haze is simultaneously doing something else that has no parallel anywhere in the solar system. Pluto's haze is energizing methane and other organic molecules at the edge of the atmosphere, kicking them out into space. And some of those escaping molecules are being captured by Charon, Pluto's large companion moon, and settling onto its poles. Charon is stealing Pluto's atmosphere, not quickly, not dramatically in any single moment, but continuously over billions of years, molecule by molecule. Pluto's haze is driving its own atmospheric material across the gravitational boundary between the two worlds, and Charon is absorbing it. The dark reddish stains on Charon's polar regions, the features that puzzled scientists when New Horizons photographed them in 2015, are Pluto's material. Organic molecules that escaped Pluto, crossed the void between the two worlds, landed on Charon's poles, and were then transformed by radiation from the sun and from cosmic rays into complex reddish organic compounds called tholins. What looks like a geological feature on Charon's surface is actually a record of billions of years of atmospheric theft from its neighbor. This interaction between Pluto and Charon happens nowhere else in the solar system. No other moon-planet pair has this dynamic where one body's atmosphere is actively being processed and transferred to the other. It makes the Pluto-Charon system something fundamentally different from every other binary system astronomers have studied. Not just two worlds orbiting each other, but two worlds in active chemical conversation across space. JWST's close study of Charon's surface added another layer to this picture. Using the near-infrared spectrograph instrument, researchers detected both carbon dioxide and hydrogen peroxide on Charon's surface, alongside ammonia and crystalline water ice. Hydrogen peroxide is particularly significant. It forms when light and radiation interact with water ice, indicating that active surface chemistry is ongoing on Charon right now. Active chemistry. On a moon more than 3.5 billion miles from the sun with no internal heat, no liquid water, no atmosphere of its own, radiation is continuously processing the material on Charon's surface, the water ice that makes up its base, the organic compounds arriving from Pluto, and generating new chemical compounds that weren't there before. Charon is not static. It is a slow-motion chemistry laboratory running on cosmic radiation, steadily manufacturing new molecules in the cold, in the dark, at the edge of the solar system. JWST's spectral observations of Pluto itself also revealed unexpected chemical richness in a wavelength range from 4.9 to 27 micrometers that had never been explored before due to instrumental limitations. What that spectral range showed was a complexity 11 minutes of chemistry on Pluto's surface and in its atmosphere that earlier measurements had not come close to capturing. Signatures of methane ice, deuterated methane, ethylene ice, and patterns of thermal emission from the haze that provided detailed information on the structure and composition of the atmosphere in ways entirely new to science. And then came the discovery published in July 2026 that stopped researchers cold. When scientists analyzed JWST spectra of Titan, Saturn's largest moon using the NI, SPEC, and MIRI instruments, they found an unexpected absorption feature centered at a wavelength of 5 quantum 13 micrometers. At this very specific point in the electromagnetic spectrum, the surface of Titan was absorbing light in a way that didn't match any known compound. The team compared the signal against every known atmospheric gas, every known haze particle, every known ice or organic compound in the scientific literature. Nothing matched. Nothing. An unknown substance on one of the most studied moons in the solar system. Titan is not an obscure, poorly understood world. It has been visited by the Cassini spacecraft, studied for decades, and is one of the primary targets of astrobiological research because of its thick nitrogen atmosphere and lakes of liquid methane. And yet, even on Titan, JWST has found something that current chemistry cannot identify. Then, the researchers checked the JWST data for Pluto observed in May 2023. They found the exact same absorption feature at 5113 micrometers on Pluto's surface. The same mystery signal appearing on two completely different worlds, billions of miles apart. The depth of the absorption is similar on both worlds, around 4 to 7%, but the width of the feature on Pluto is roughly 3 times broader than on Titan. Same molecular fingerprint, different width. That difference is scientifically interesting, rather than confusing, because it tells researchers something about how the compound behaves differently under the distinct surface conditions of each world. Titan has a thick atmosphere and liquid methane lakes. Pluto has a thin haze atmosphere and nitrogen ice plains. The fact that the same substance appears on both worlds under very different conditions suggests it is something that can form through a common chemical pathway that operates across the outer solar system, not something requiring a very specific local environment. Scientists are now running laboratory experiments to test whether candidate molecules, when mixed or altered under Titan and Pluto conditions, can reproduce the mysterious spectral fingerprint. The lead researcher noted that mapping the distribution of this compound on Titan's surface could reveal whether it correlates with geological features like the vast dune fields that cover much of Titan's equatorial regions. If the mystery substance is concentrated in the dunes, that tells you something completely different about how it forms compared to if it's spread uniformly across the surface. The NASA Dragonfly mission, a nuclear-powered rovercraft designed to fly through Titan's thick atmosphere and land at multiple locations on its surface, is scheduled to launch in 2028 and reach Titan in 2034. When it does, it will be able to directly sample and chemically analyze whatever this substance is. But that is 8 years away. For now, an unknown molecule exists on the surface of at least 2 worlds in our solar system, and science genuinely cannot tell you what it is. Now, step back from the specific findings and look at the bigger picture of what all of this means together. Because Pluto orbits the Sun once every 248 Earth years, the JWST observations from 2022 and 2025 are sampling only the very early stages of what will be a long Arctic winter at Pluto's North Pole as the dwarf planet moves further from the Sun along its elliptical orbit. Scientists expect the haze thermostat to work even harder as the Sun gets dimmer from Pluto's perspective. And JWST will be able to test that prediction across the next decade of observations. This is enormously significant. For the first time in the history of Pluto research, there is an instrument capable of watching Pluto change in something approaching real time. Not on geological timescales, not over centuries, over years. The timescale on which a single observatory mission operates. James Webb can return to Pluto every observing season and measure how its atmosphere is evolving as the planet moves through its orbit. The physics that controls Pluto's climate can be tracked directly compared to predictions and used to refine our understanding of how haze-dominated atmospheres work. The implications stretch far beyond Pluto itself. The chemistry and radiative effects of the haze found at Pluto could also be occurring in other tenuous atmospheres, rich in nitrogen and methane, including Triton, Neptune's clear throat, largest moon, the upper layers of Titan's atmosphere above the thick lower layers, and potentially some exoplanets. Pluto now serves as the first natural benchmark for this category of atmospheric physics, exoplanets. This is where the connection between a frozen dwarf planet billions of miles away and the cutting edge of modern astronomy becomes clear. One of the biggest challenges in characterizing the atmospheres of planets orbiting other stars is interpreting the spectral signatures of hazes. When James Webb looks at an exoplanet atmosphere and sees haze, the scientists interpreting that data need physical models of how haze works to understand what they're seeing. Until now, those models were built on theory and laboratory experiments. Pluto is the first real natural laboratory, a world where haze is the dominant atmospheric force, observable with the same telescope being used to study exoplanet atmospheres, allowing direct comparison and model validation that was simply impossible before. And then there's the connection to early Earth, before oxygen transformed our planet's atmosphere. Roughly 2.4 billion years ago, Earth was wrapped in a haze of organic particles. Nitrogen and hydrocarbon chemistry, strikingly similar to what exists at Pluto today. That early haze may have played a role in stabilizing Earth's temperatures and fostering the conditions in which early life could develop. Studying Pluto's haze and chemistry might give scientists new insights into the conditions that made Earth habitable in the first place. The lead scientist on the JWST Pluto haze paper said this directly, not a speculation, as a scientific motivation for the research. Understanding what is happening in Pluto's atmosphere right now may help answer one of the oldest and most fundamental questions in science. How did life get started on Earth? This is the full arc of what James Webb has revealed at Pluto, a world that was a blurry point of light for most of human history, that got its first close-up look from a spacecraft that flew past it once and kept going, that was stripped of its planetary status and dismissed in popular culture as an afterthought. That turned out when the right instrument finally looked properly to host a climate system found nowhere else in the solar system. An atmospheric haze that acts as a planetary thermostat with no parallel anywhere else. A companion moon being continuously fed molecules stolen from Pluto's own atmosphere. Active radiation chemistry on that moon generating new compounds in the cold and dark. An unknown substance on its surface that also appears on Titan and matches nothing in the catalog of known chemistry and connections to the origin of life on Earth, and to the interpretation of atmospheres around planets orbiting other stars. James Webb was not supposed to be able to study Pluto in meaningful detail. The original design priorities of the telescope were focused on the early universe, on galaxies forming in the first few 100 million years after the Big Bang, on nearby star formation regions, on exoplanet atmospheres. Pluto was not in the original sales pitch. It was too small, too cold, too dim, almost too challenging, even for Webb's extraordinary sensitivity. But the telescope's performance in space exceeded expectations. Its mirrors aligned more precisely than required. Its instruments proved more sensitive than their design specifications. And scientists who had spent years thinking about what JWST might be able to do, if pointed at the outer solar system, decided to try. They pointed it at Pluto. And Pluto turned out to be one of the most scientifically productive targets the telescope has ever observed. The universe keeps doing this. Every time a genuinely new instrument arrives, with capabilities meaningfully beyond what existed before, it finds things that weren't supposed to be there. Not because reality is strange, because our models of reality are always incomplete. The data is always richer than the theory. And the places that seem least promising, the small frozen worlds at the dark edges of the solar system, often turn out to be the ones hiding the most. Pluto waited 95 years after its discovery for a telescope powerful enough to read what was written on its surface and in its atmosphere. James Webb finally did it. And what was written there? A unique climate, a living chemistry, an unknown molecule, and a connection to the question of how life on Earth began was worth every year of waiting.